Hello, everyone. Thank you for joining me today for doing a little last minute studying for COE818. This is going to be kind of the outline of what we're going to do today. We're going to first of all do the loop unrolling question because she's making a big deal about that. And then we're going to talk about the state diagrams just to know. Okay. And then we're going to talk about any, just general other things that may be on the exam. Right, so there's probably going to be some kind of pipelining question that's going to be involved. Yeah, so we'll go for definitely maximum 2 hours, hopefully less. Try to get everything done. And if anybody has any questions, as usual, just unmute or type in the chat. I'll have the Zoom chat open. Or if you have something to send me, just send me on Discord. You got the Zoom link from Discord, so I'll just assume you can send me stuff on Discord. And yeah, okay. So any questions before we start? Anything in particular you want me to do? Anything you want me to like add to this list of things to do here?
Could you also go into detail on a few things and also maybe explain a little slower sometimes?
Sure. Yeah. I mean, if there's anything but you got to tell me when there's something that you want me to explain better, right? So if there's anything that is confusing, just let me know. I'm happy to explain better or slower.
Just the the MIPS. The MIPS and the MIPS and the unrolling. The process where we write install,
Right. So I'm gonna do loop unrolling, absolutely, and then MIPS is kind of the whole thing, right? We're talking about MIPS pipelining here, so it's gonna be the whole kind of thing here. But yeah, definitely.
Okay, thank you.
Of course. So why don't we start by looking at the loop unrolling question? So that's in review and then loop unrolling. So why don't we try to make sense of it together here? So you just look at the document together here. So loop unrolling is basically the idea is like when we have we can get better throughput if we handle multiple iterations of the loop at a time and then just iterate through that, right? And it basically we get better use of our different registers and all this kind of stuff, less stalls, and the overall cycle time and stuff like that. The performance gain is good when we have both loop unrolling and scheduling. But as she described in the lecture, the question is most likely going to start with just something very similar to this, right? And you're expected to just write the MIPS code, then write the performance, as in include the stalls, right? So write where the stalls are as well. And I know this is a point of confusion today, right? So people are talking about that in the chat, so we'll talk about this. I mean, I understand why the loops. I basically just think this should be 3 cycles. That's my only thing. I just think that should be 3 cycles. Anyways, we'll talk about this. These numbers, I think, whatever. We'll talk about it in a second. And then using scheduling, right? So you can kind of reschedule some of these operations. Stall 1 cycle, for cycles, and then doing loop unrolling, and then loop unrolling with scheduling. So let's just start with the actual code. So the actual code is here. Oh yeah, and I guess I'll add onto this list like doing it with vector processing too, right? That's also something that we'd like to do as well. There's a sample exam that does that. So first of all, let's write this just writing the MIPS code, right? MIPS. So we are doing a for loop. We're iterating I1, I equals 1, 1,000, looping 1,000 times, right? We're looping 1,000 times from essentially x1 plus this constant s here. I'm assuming this constant s, we're assuming everything here is a floating point, and this s is stored in F2. And also that R1 is initialized, right, to be the address of this, right? I guess, R1 is initialized to be the address of this in memory. So memory R1 is x 1,000. The reason you see this here it's really your choice by design, but you can either go forward through the loop or you can go backwards through the loop. It doesn't really matter because there's no like interrelationship between the different stages, the different iterations. So we're actually going to go backwards. It's a little bit more efficient if we just go backwards. So we start at 1,000. You see how like R1, it starts at 1,000. And then we go backwards through the loop from there. It's R1 is the, so to be clear, R1 is not equal to 1,000, but it's like the memory address of X 1,000. So yeah, so the first thing in the loop that we need to do is we need to load, right? We need to load in this xi. Right? So we're going to just do load. It's a floating point, so we do LD. It's not load word, but load LD. And then we're going to load in into register. We'll just choose a register, say F0, and from location 0 R1. And it's always 0 R1 because R1's the memory location. So that the point of this is that we have that F0 equals Xi. And then we're gonna, this is the loop, and so then we loaded it in. So then we need to add now, and so to add, we're putting 3 Ds because it's add data. And what are we adding? Well, we're gonna put it in. It doesn't really matter where you put it. You could put it back in F0. It doesn't really matter, but I'll match the solution. So F4, and we're gonna add F0 with F2, and F2 is S. So this is taking F4 equals that result plus S. Then we need to just store this, SD, right? We first tell it where we're going to store it. So we're going to store it 0 R1. And then we are storing it. What are we storing? We're storing F4 there. So that's that. Then the last thing to do is we need to change the R1. So remember, we're starting at 1,000, right? We're starting at, well, it's not really 1,000, but it's the address of value 1,000. Right? And we're gonna keep just going backwards, right? So it's sub I. We're gonna subtract immediate. I'll just do capitals. I don't know why it's lowercase. Sub I. Right? And we need to keep subtracting the size of the data, the size of xi. Well, xi is a float, right? Float. So that's 64. It's a double. It's a D for, we're assuming it's a double precision float. I guess that's kind of just assumed. But anyways, a float is generally 64 bits. A double is 64 bits. So that means it's 8 bytes. 64 bits. So we need to go backwards by 8. So that we're going to do that to R1. R1, 8. And we're going to just keep subtracting that. And we're just going to keep doing that until, so branch not equal to 0, R1 loop. Right? So as long as R1 is not 0, we're going to branch back to loop. And once it is 0, then we've done the correct amount of iterations. And we're assuming that R1 is initialized properly. We did not initialize R1. Right? We never said it, but we're just assuming R1 is initialized correctly. You could just write that on the test. You can just say, assuming R1 is initialized to have the correct address, and assuming, S is in F2. Like you just write that. You don't need them to say it. You can just write that. And there's our code. So hopefully that's okay. Now we need to see where the stalls are going to be, right? With just a standard, we can have forwarding, right? There's like forwarding is fine, but we can't, but there's no loop unrolling and stuff like this, right? So let's give it a shot, right? So to do this, to figure out where the stalls are going to be, we have to draw a Gantt chart. We have to draw the actual thing, right? The actual chart. So I'll maybe switch to this, right? So to draw the Gantt chart, we're going to load, I'll just write it again, F0, 0, R1, and then we're going to add F4, F0, F2, and then we're going to store data 0, R1. I'm just rewriting the code here, F4, sub I, R1, and then subtract by 8, and then B, N, E, Z, R1 loop. Okay, so there's our code. Now we're going to start, of course, just F1, fetch, decode, execute, memory, write back. Great, that's a 0, F0. Then fetch, decode, according to our professor, will always go, but then the execute stage for add, well, the execute stage for add depends on the result of F0 here. And we can use forwarding. So this result is available to us at the end of the mem stage. So we need to stall once. We need to stall once here. And then what we can do is we can grab, we can now do the execute for 2. So we had to stall once because the forwarding from memory to the execution stage. This is available at the memory stage. It's a floating point addition. Floating point addition takes 4 clocks, if I recall correctly. That's a key thing, if I recall correctly. Why don't we just verify this quickly? Okay. Let's duplicate this tab. We can go back to our lecture. We can go to pipelining, and I think it's near the end here. I think maybe I passed it. No. There it is. Addition, floating point addition takes 4 clocks. Right? So it's going to be E2, 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 like that. Floating point addition takes 4 clocks. Okay, so now we have this. Okay, well, sorry. Then we still have memory 2, write back 2. Then fetch 3, decode 3. Okay, now what? We're storing the result of F4 in our 0R1. So we can do execute 3. That's fine, right? Because what is execute 3? Execute 3 is 0 plus R1. That's all execute's doing. But the memory stage needs to stall 2, I guess. 1, 2. Yeah, 2. Why did I get 3 before? I distinctly remember getting 3, but maybe I did it wrong. I don't know. So fetch, decode, execute. Now we can. Oh yeah. I can't do because why I can't do mem 3 at the same time as mem 2. Well, I guess you can because this is not actually using the memory module. But I don't think we can make that assumption. It's hard to say. I think the solution might only have 2 stalls because they're saying you can do M2, M3 at the same time.
Wait, if I may ask again,
yeah,
wasn't there supposed to be a stall in front of the, the second execute, behind the, wasn't there supposed to be a stall behind on the second execute after the first one instead of the last? Yeah.
Like you're saying there should be a stall like right here?
Yeah.
Why should there be a stall?
I thought like there's the first execute, but like I think there's a few. Sorry, like there's the. I thought there was supposed to be like a pattern or something.
Well, the pattern is that there's 4 executes for a floating point add, right? There's like a floating point add. So for a floating point add, there's 4 executes. But in terms of stalls, you only stall if there's like a data dependency, like you have a read after write. So for example, we had to stall here because the result of this execute or the result of this memory had to go to the execute. And we had to stall here because the result of this execution has to go to the memory. So we had to wait for that. So stalling is whenever you're like waiting for things.
Right.
So then the thing that I was saying is just like that I think there has to be another stall here because I don't know. This is really kind of wishy-washy. So if you put this here, just say that I can do M2 and M3 at the same time because M2 there's no M2. Like this does not access M2, right? There's nothing happening in the memory module. So it's fine. You can just have that. You use add with 3 Ds to be when it's like a double. So like a floating point. We're using floating point and double. They're all double. Anything that's not an integer is a double. So it's you use add same reason we're using load and store data. because it's like it's not a standard word size. Otherwise, you'd use load word and store word and all that. Okay, so according to mul d, I guess you would say that as well. Yeah. So assuming we can just put this here because there's nothing actually happening. Well, the write back stage is happening. Oh yeah, but then the write back stage of this isn't happening. There's no write back stage here, right? So technically those can go together, and then you have F4, F4 execute 4. No, what am I saying? Decode 4, execute 4. What is this? This is sub I. Yeah, this is completely independent of everything, right? So load, decode, fetch, decode, execute, memory, write back, and then finally we have fetch, decode, execute. There's really no execute stage, but anyways, execute. No, execute. This is the whole discussion. Okay, so, in the solution she stalls after added. In the solution she stalls after added, and that's because you can't have M2 and M3 on the same cycle. Is there a stall after add? There's a stall after add because of this, or before add. Wait. What's the solution saying? Like, you're saying this solution? Like this guy? These two stalls? That's what you're referring to? I think so. Those two stalls are like these two stalls, right there, like that. So you need to stall twice after that, right? So that's why. And then someone's asking, why does W3 and W2 not conflict? I mean, I agree that in general they should conflict, but add is doing W2, right? It's writing back to that register. Store data, well, it doesn't actually write back anything. It's not writing a register at all. It's just writing to memory. So it doesn't actually need that, right? Yeah. It doesn't actually need that W3 stage. It's not doing anything in W3. So W2 can go, and just like M2, nothing's happening in M2, so M3 can go. I'm assuming this is why there's only 2 stalls here rather than 3 stalls, which is what I thought there should be. Honestly, I think if you just explain this, if you just write this in words on your sheet, it's fine. E5. No, sorry, this is the whole thing I'm discussing. I keep losing my train of thought. So this BNEZ R1 loop, well, what does it need? It needs the fetch stage. The decode stage can only happen once the execute is done. So there needs to be one more stall here right before the decode stage, because the result from the execute is being sent to the decode stage. The decode stage is where BNEZ does its computation. That's where it checks 0. Because it can't do it in the execute stage. The execute stage is calculating the branch address, calculating what you're branching to, right? E5, fetch, decode, execute, memory 5, write back 5, right? So it can't do it there. So it must do it in the decode stage. Otherwise, you need 2 execute stages. So that's why we need a stall here to forward this. And then there's always a stall after BNEZ. There's always a stall after, unless you reschedule it and you put some line of code there. Like, for example, you could put sub I there. No, I don't know if you could put sub. You could probably put store data there. So technically one more stall there, right? And so the total time is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have 14 clocks. These numbers along the side, to be honest, I don't know what they're talking about. Because it's not like
these are the number of 10 clock cycles, you know?
But like, what exactly does that mean? Like, this doesn't take 10 clock cycles. Like, it's 1 clock. This doesn't take 8 clock cycles.
Actually, it's counting by 1.
So yeah, so I guess it's like one. It's just like, I think it's just like labeling like at what clock does it start? Maybe is what it's saying. That's probably what it's saying. It starts at clock 1 to clock 3. But does that start at clock 3? It doesn't really. But I guess that's the no-op. Yeah, that's the no-op you're putting in there. So I guess it's saying what clock it starts at. But that doesn't necessarily correspond with where our F2 is here, because our Gantt chart is kind of like... Because when you put a stall, you're not like that's not what's actually happening. That's just how we represent it. You're really putting a no op. That's what's happening. You're inserting a no op in between here. So basically, there's right after, like, just looking at this code right now, there's going to be a no op, a stall, one stall right there, right? Because of that. Then here, that doesn't get counted again. That's just the stall from before. But now we have to insert 2 more stalls right after addeda. So 2 stalls, 1 stall here, 2 stalls there. And then right after added, there's 2 right before. So then right here, there must be 1 more stall right there, right? Because we had to insert the stall. So since we inserted that stall right there, it goes right before the instruction goes, because there's a no op. What we're saying is there's a no op happening right before. And then there has to be a stall. There's always a stall at the end. Because the branch has a branch delay slot. So you can't fetch the next instruction. Right? You can't fetch because you don't know if you're fetching until here. This is where the next time you can fetch. So you have to stall. So there we go. There's our pipelined with forwarding, but no loop unrolling, nothing else, right? So it's going to be the exact same code. I'm not going to rewrite it. I'm just going to move this here. And then I'm just going to insert the stalls, right? So there's a stall right here. There's 2 stalls right here. There's a stall right here. And there's a stall at the end there. So I'm just going to say stall. I'm going to say stall, stall. There's a stall here, stall. There's a stall here, right? So we're inserting 1, 2, 3, 4, 5 no ops. 1, 2, 3, 4, and then 5 at the end, no ops. So there we go. So that's that. That's the second part of the question, right? So that's getting the performance like that.
Wait, so if I may ask again.
You may. Go ahead.
So about the stalls, like, how do you know the stall appear? How do you know when to put the stalls there again?
Like these guys? These things?
Yeah.
Yeah, well, whenever you have a data dependency, right? So like here, I had to put this one because I can't do execute 2. I can't start the execution because the execution needs F0. Right. When do I know F0? I know F0 right at the end of M1. So right at the end of M1, I can forward this. I can forward this value to E1. So that's why, but I can't do it I can't do it a clock earlier, right? I have to do it at clock 5.
Okay.
And all of the rest of them are the same reasons. It's all just there's a data dependency, right? So this I had to forward this here, and this I had to forward this here. This last one's kind of tricky. The last one is just because BNEZ, it checks if R1 is equal to 0 at the decode stage, not at the execute stage. So you need it at the decode stage.
And okay, so if I were so there's like a 1 stall, then another stall with 2 stalls, and then 1 other stall and the other stall in between. That makes it like 5 cycles. Then you're also adding the MIPS code as well.
Like this is the MIPS code here, right? I'm just putting the stalls in between the MIPS code. Like let me highlight here, right? So like that stall is that stall. Those 2 stalls are those 2 stalls.
Okay.
That stall is that stall, and then finally, there has to be a no op at the end of after branch. There's always a no op.
Okay. Thanks.
No problem. There you go. Okay, so let's move on. Let's try with scheduling now, right? So with scheduling, that means we just like to reorder this a little bit so that the data dependencies can kind of do their thing a little bit, right? So one thing we could do is that this sub I right here, it doesn't need to be there, right? This sub I could be moved anywhere, to be honest, right? And then that would get rid of this stall, right? Because if we could just do it earlier, then we don't need this stall. The only reason we have the stall is because we're just calculating that before. But what if we switch these 2 places? In fact, what if we put sub I here, right? Or even right at the start. Usually the thing we do is we do it right at the start. And the reason for that is it's going to get rid of that stall, and then it's going to get rid of this stall as well by doing that. I think we'll still have a stall here. I don't know how that's going to be dealt with. Oh, let me look at the solution here. So stall 1 cycle. Okay, this is just what I would do. I think the solutions are wrong sometimes, so I'm just gonna write what I would say. So this is forwarding without scheduling. This is plus scheduling. Okay, so the first thing is we'd have loop, and then the first thing we always have to do is we have to load F0 0 R1. What we can do next, to get rid of this stall right here, is we could do the sub I, because the sub I has no dependency on anything, right? So then we can do the sub I R1 R1 8. Okay, then what can we do? Well, we can add immediately. No stall anymore, right? We can just add F4 again, F0, F2. Okay, now there may be some stalls in here, so we'll talk about that. But then what's left to do? I mean, there's just store data. Well, yeah, there must be some stalls. Looking at the code here. Well, actually, we need to use the branch delay slot. Yeah, we need to use the branch delay slot. So I could just say BNEZ R1 loop. And then to fill the branch, okay, so again, there might, I don't know, there's some stalls in here, right? So stall maybe, question mark, right? But there definitely is some branch delay slot at the end here where we can do the sub I. I think maybe, or SD. I think maybe this might have been a typo from the professor. So 8, no, negative 8. No, 8. 8 R1 F4. Right, so what are we doing? We're doing the same thing as before here, but instead of being at exactly location R1, I'm going location R1 plus 8 because I already subtract. You see here I subtract after, but I subtracted before. So to counteract that, we just have an 8 there. It could be 8 plus. We're going to add that back. So for some reason, the solution has a stall here. I think maybe that's incorrect. I think the stall is supposed to be here. I think that's a typo. I think the stall is supposed to be here. But the only way to verify that, to be honest, is drawing a Gantt chart, which is a little unfortunate because that takes forever, but let's just do it quickly. So I'll just number the instructions. 1, 2, 3, 4, 5. So instruction, let's start it here. 1. So maybe I'll just go like this. So instruction 1 has a fetch, decode, execute, memory, write back. Next, fetch. Someone's asking a question. Can you re-explain the last part for, the 8? Yeah, so here, right, let's think about the value, right? Like, let's trace R1. Let's say R1 is equal to 20. So here, right, nothing happens to it. Here, we're doing SD at 0 plus 20. And then here, R1 equals 12 because of that line. Is that okay what I'm saying with this? And then here R1 equals 12 for the branch as well. So hopefully that's okay what I'm saying, because I'm just tracing the value of R1. I'm just suppose it's 20. Like that, I'm just starting with that. Like suppose it's 20. Then here we're doing 0 plus 20. And here it's going to be 12 now, and so it's going to be 12 for the branch. So now let's trace it here. Let's suppose R1 is 20. Well, now R1 is 12. Okay, here R1 is 12. Great, that's what we wanted, right? We wanted R1 to be 12 for the branch. But here we don't want R1 to be 12. We want it to be 20. Okay, I'm just going to add back. It's going to be store data at 8 plus 12, which is 20. And I get the same thing, right? Because we have 20 here and we have 20 here for the store data. So in both cases, the store data is getting the 12, is getting 20. Yes, 8R10 is adding R1 is adding 8 bracket R1 is adding 8 to R1. If the BNEZ condition is met, does it cut the loop at L1 or after SD at I5? No, regardless of the branch condition, the instruction after the branch will run, regardless of if the branch runs or not. So hopefully that answers the question, right? Yeah, it cuts the loop after SD at I5. I5, like the fifth instruction will always run after the branch. That's the point of the branch delay slot, because otherwise you just wouldn't know what the next instruction is. Like there would be 2 branch delay slots if we didn't do this whole decode thing, right? But there's only 1 at least. Or you'd have to just change the architecture entirely to allow for no branch delay slots. It'd be interesting to see how you could change the architecture to make it have no branch delay slot. I don't know how you do that, but anyways, little project. So instruction number 2, we have F2. Now let's think about it. To do this, do I need any dependencies? I need nothing, right? F2, this is just going to be decode 2, execute 2, mem 2, write back 2. Perfect. Nothing happened there. Then F3. 3 is the addida. Addida. That's available at the end of... Let me just think for a second. That is available at the end of fetch decode 2 at the end of M1, which we have right there. Perfect. So that can just be forwarded. And then we have execute 3, execute 3, execute 3, execute 3, right? Because it's a floating point, so we're going to have 3 execute stages. Mem 3, write back 3. Okay, now we're going to get a stall now, I think. So number 4, right? We have fetch 4, decode 4. Okay, so decode 4, no, we don't have any stall. Because what does decode 4 need? Decode 4 needs the value of R1. The value of R1 can just be forwarded. Right there. Can just be forwarded. So then we have that. Fetch, decode. Yeah, the value of R can just be forwarded. And then we have execute 4, memory 4, write back 4. And then, you know. Oh, is there a stall here? 5. Oh, there may be a stall here. 5. Oh, that's kind of weird. Anyway, okay, so that's kind of weird. But yeah, execute. So F5. And then you'd have decode 5. Execute 5 is fine. Execute 5. Write that better. Execute 5. Why? Someone's saying there should be a stall at I3, I4. Where should it be? Why? Or Andre, you're saying it. Why, Andre? Is there a stall at I3 or I5? I3, I4. Fetch, decode, execute. So I4. Well, I4 just needs the value of R1. That's all I4 needs, the value of R1. And the value of R1 is available right there. So that can just be forwarded right there to that. H plus R1 is the execute stage. And then the mem stage needs the result F4. The result F4 is not available for 1 additional clock. Right? That's where F4 is available. So then we can do mem 4. And then we can do write back 4, again, with the assumption that they can be done at the same time, concurrently, because they use different modules. They don't use the same modules. Okay, so that's where we have 1 stall, and this stall comes from here. Okay, so it's weirdly notated. Technically, we need a stall here, but you wouldn't put the stall here. You'd put the stall here, because there's a single branch delay slot, right? Like, you're not going to put the stall there. You technically would put the stall here, but at the end of the day, it doesn't matter where you put the stall in terms of latency and in terms of performance, right? It just matters in terms of correctness of the code, but that's just like whatever, syntax stuff. So basically, whenever you see code written, just assume everything after the branch will run. So even if it's like 2 spots, technically that doesn't really make sense. But it's okay because you can just put, what we're actually going to do is we're just going to put the stall before. We're just going to stall it there. And then we're going to do that. So the stall at the end of BNEZ can be replaced with instruction. Definitely. We definitely want to do that because there has to be a spot there. There has to be an instruction after branch. So you may as well make it do something useful. So you definitely want, that's the point of rescheduling or scheduling, right? Is that we do that there. But yeah, exactly. You're right. Okay, so that's why we have a stall hanging out there. That's why there's a stall 1 cycle. You find all these stalls, just draw the chart, right? It's not the easiest thing to draw the charts, but it's also not too bad to draw the charts. That usually clears things up, like why we have these things. So the number of cycles is 1, 2, 3, 4, 5, 6. Here the number of cycles is 1, 2, 3, 4, 5. No, sorry, that's not a good thing because that doesn't have stalls. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, right? So we've got some improvement here by just rescheduling a little bit. Okay, let's do some loop unrolling, right? So the next thing is loop unrolling. So unrolling the loop 4 times will get us a better average throughput. So the point of loop unrolling, first of all, assumption, it'll give you how many loop unroll into how many segments. We're going to loop unroll into 4 segments here. But additionally, loop unrolling, you just assume that the amount of iterations of the loop will be divisible by 4. That's kind of my point. Like, you don't have to really think about that because, it technically doesn't have to be, right? So then you'd be screwing up the loop unrolling if you did it. But anyways, we just make some simplifying assumptions that you can just break it nicely into chunks of 4 and it'll all work out nicely. And so we do this based off of the rescheduled code. Or not the rescheduled code. No. Based off this code, right? So based off of this code, no scheduling, right? Based off of the no forward with no rescheduling code, right? We do this. So let me maybe take a screenshot of this just so I have it here. I guess I'll erase all this stuff. And then I'll erase all this stuff too. We don't need this here. Okay. So I'll just take a screenshot of that and I'll put this just in the corner here just so we can kind of, we don't have to scroll up and down all the time. Maybe I'll, just for legibility, I'll put it in a little box. Okay. So we're going to loop unroll 4 times. Unroll 4. So it starts off the same, right? So we're going to have our load. We're going to load. And you just choose some registers, right? So we're just going to load F0, 0R1. We need a stall for the same reason we need a stall before. Then we added a F4, same as before, F4, F0, F2, and then we double stall. And then we store data. Oh, we don't, yeah, we store data. Yeah, we store data. 0R1, F4. And that's the first iteration of the loop. And it's at this point, and we can say loop here. This is the beginning of our loop, right? It's at this point that you would usually increment or decrement, in this case, R1 and then branch, right? But we're not going to do that. We're just going to start the next iteration of the loop. And so how do we do that? Well, we load F0. And now, what are we going to do? We're going to the next element, right? Remember, what do we do every iteration? We subtract 8 from R1. So I'm just going to manually do that. Subtract 8 from R1, load that into not F0 anymore, some other register, F6, let's say. And this is the point. We're going to use all the registers, right, to do multiple at the same time. Well, not necessarily all of the registers, but many of the registers to do a bunch of these at the same time. There's no stall here, by the way. I'm just like putting a little division line just so that we have a spot there. And then the rest of this is the same. F6, or no, whatever. I'll just use whatever they use here. F8, F6, F2. Same thing as before. We stall twice. Then we store data. Again, this is going to be at -8 R1 F8, right? Because we don't need we don't need to store it at R1. We need to store it at 8 below R1 because that's this next iteration. And then again, I'm just like, it's just exactly the same thing again. And then it's going to be exactly the same thing one more time. But that last iteration, we're going to have some small changes. So this one, boom, boom, boom. I'm going to change just, maybe I'll use a different color just so you see what I'm changing, right? I'm just going to change just the names. So this is 0, this is 0, this is 0, this is 4, this is 0, this is, this would be F4, right? And then this one is a 6 now, and this is -8, and this is an 8, and this is a 8, and this is a -8. This time this will be some other number, let's say 10. And this is -8 still, and this is, let's say 12, and this is 10, and this is, sorry, this is not -8 anymore, it's -16 now. It's -16 now. So the, we put that there, and then we put the F12 here, like that. And yeah, so there we have that. So yeah, so -16 this time because we're going 8 lower again. And then the last iteration is going to be -24, -24. Just put it a different register again, right? So let's say we put this into, what does he use? I'll just use the same thing. F14, F14, F16, F16. It's the same thing over and over and over again, but we're just changing what registers we're using, and we're just using a different offset of the current R value. Now, we're not done because we still need to loop back. We haven't done everything. The loop has to run like 1,000 times. We've just done 4 at a time. So now we got to loop back up to the top. But we also have to decrement our R1 value. So we're going to do sub I, and R1, right? We're going to sub I, R1. But what we're going to subtract is 32. And the reason we're going to subtract 32 is because we want to start at the next element right after this. Let's say we only subtracted 8. If we only subtracted 8, then we'd just be doing this element again. If we only subtracted 16, then we'd just be doing this element again. And if we only subtracted 24, then we'd just be doing this element again. So we need to subtract 32 to get to the next element there. Okay. And then for the same reason as before, we need a stall here, right? Just because we had a stall. So we need a stall for the same reason. BNEZ R1 loop. And then we have a stall right here. There we go. And a thing you should just make sure of, well, I get, yeah. A thing that you should just make sure it makes sense in your head is that there's no dependency between this and this, even though they're doing the same operations. It's just because they're using different registers, right? If they use the same registers, then we're not really doing anything if we're using the same registers, right? Then we're just kind of writing it all out. The whole point, because we are just kind of writing it all out right now, the whole point is that you can now reschedule this. You can reorder all of these as if they're just one big program, getting rid of basically all the stalls. So that's the next and final part of this, is that we reorder this or reschedule it to get rid of the stalls. And the basic idea is you just do all the loads right at the start. You do all the adds right at the start. You do all the store words right at the start. And then you have to a little bit, mess around with where you're going to getting rid of these stalls, right? So you have to do maybe something slightly different with that, but it's essentially the same thing. So let's just start rewriting it. So the first thing is I'm going to put all the loads at the start. So we're going to have load F0, 0, R1. And then we're going to have the next load. Load, so 0, F6, -8, R1. And then we're going to load F10, -16, R1. And then we're going to load F14 negative 24 R1. There's all our loads. Then we need to do all our adds. So add F4, F0, F2, no stall needed anymore, right? Because that needs to go there, but that's way far enough, right? That's way to the side. So no need for that anymore. No need for no need for this stall, essentially. Okay. These stalls were needed. Why again? Oh yeah, because this dependency like that, and that again is also going to go away. So anyways, but we're not there yet. So added and then the next add F8, F6, F2. And then the next one F10, no, F12, F10, F2. And then the last one added it's going to be whatever, 16, F10, F2. Right? 16, F14. What am I saying? 14, F2. Okay, so we've done all that. No stalls needed, right? No stalls needed. Maybe just for visual sake, I guess I can't do that. For visual sake, I'll just put a little space here just because there was a space. Just so we can count the instructions equally. Right? Then the next one, did I stay consistent with my... No, I did not. I will just move this up a little bit. There. Why is that there? Okay, I'll kind of have to squeeze these together just because I want to stay consistent with like how many blocks I take. There you go. That each instruction gets a block. So there's our 4 adds. Now we have to ask ourselves, can I do the SD? Well, I can, right? Because SD 0R1 F4, well, is F4 available? F4 is going to take a while for F4 to be available, but you can draw the Gantt chart if you want, and you can see that F4 will be available at this time. Because how many clocks does it take, right? It took 2 additional stalls. Well, we definitely have those 2. We've more than that. We have 3 additional stalls. So we have the time. Same reasoning. We don't have to wait for SD negative 8 R1 F8. And we don't have to wait for SD negative 16 R1 F12. And we don't have to wait for SD negative 24 R1 F16. Okay, but then now we have our branch to do, right? Or we have our sub-I, R1, R1, 32, and then we have to stall after this, and then we have our branch, R1 loop, and we have a stall after this. So this is actually not ideal because we still have 2 stalls. We can get rid of those stalls. And we can get rid of those stalls by... we could just put one of these store datas, put one of them there, and put one of them there. We'll have to slightly modify the code, though. F16. Where are we? Yeah, we'll have to slightly modify the code because that's not going to be... These numbers aren't going to be the same anymore because we already changed the number, right? Okay, but anyways, we'll do that. So this is going to be, change this bottom section to be, I'm taking 2 of them, right? I'm taking 2 of them here. So the next thing we do right after this is we sub-I. Right, so this is all the same. Everything's the same above this. Nothing changes above this, right? The first thing we do is we sub-I R1, R1, 32. The next thing we're going to do is we're going to do one of the store datas, SD. And for the store data, we're going to do this one, right? So I'm going to put that one there. So it's going to be, well, it's not going to be minus 16 anymore. It's going to be something R1 F12. Okay, so we got to think about what's happening here, right? R1 is, let's say, at 0. Okay, then we are adding, subbing 32. Okay, let's say R1 is at 32. And then we are subbing 32, and we're getting to 0 here. Right? Originally, we wanted this to be at minus 16, right? F12. I think it's supposed to be plus 16. Yeah, I think there's a mistake there. Yeah. We wanted it to be at 16, just according to this, right? It was 32 minus 16, which is 16. Right? That's where we want it to be. So now, we're after this, we have to add 16. So this should be plus 16. It says minus 16 in the solution, but I think that's wrong. Because then it says plus 8 for the bottom one, which makes sense. But anyways, it's going to be 16 here now. And then we have our B, N, E, Z. R1 loop. And then we still have a stall because we still have one more instruction to put there, right? I guess I'm actually going to put this a little lower just to stay consistent with my spacing. Put that there instead. And so I have my B and E set, and I still have one more store data. This used to be at minus 24, which would put us at 8. Now we're at 0, so we got to jump back up by 8. So it's going to be 8, R1, F16. And there we're done. So how many clocks does that take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 clocks. And that does match with the solution. So 14 clocks for 4 instructions. Right? We didn't just do one instruction or 4 iterations of the loop, I mean. That's what I mean. So 14 divided by 4, that's only 3.5 instructions per iteration through the loop. And if we look at our original thing, we had 1, 2, 3, 4, 5. So quite an improvement, right? On average, we've gotten rid of 1.5 instructions. And this is because of the clocks. Well, actually, no, yeah, even more than that, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It was really 10, right? So it's much better improvement here over this. There is our loop unrolling question. That took a little while. I was trying to go through a little bit fast, but it still took a while. But that is our loop unrolling. Vector. Yeah, good thing I wrote that at the top. With vector operations. So let's do this with vector operations. It's really not that hard. Vector operations are not that difficult. So it's a completely different thing. We just want to find the number of clock cycles here. Right. So for the vector stuff, like you need to know a little bit more information. Like it has to tell you a little bit more information about what's happening. So for example, it has to tell you how many elements are in a vector. Right? That's one thing it has to tell you. If we just assume we can load the entire thing into a vector, if that's our assumption, that the vectors can be of size 1,000, then all this would be is load vector. Let's think about this for a second. Load vector into v1 0 r1, assuming r1 is the correct address. Add vector v1 v1, and then we're going to assume that in v2 we have the s stored, and then store vector v1 0 r1 v1. Like that, and that's it. Assuming that the entire 1,000 length thing can be loaded in. That's not always a valid assumption. Most of the time, it's like there's 64 elements in the vector. Let's say there's 64 elements in the vector, and let's say this is 1024 just to make it work out properly. So then we have to think about how many times do we have to loop through this? Well, we have to loop through this 1024 divided by 64 times. Okay, 1024 iterations divided by 64 elements. And this is elements per iteration. Right? 64, yeah, elements per iteration. Right? So this is going to be 1024 divided by 64 is 16 loops, I guess. Let's call it loops or iterations. I feel like the units don't work out there. Why do the units not work out there? 1024. Oh yeah, it's not 1024 iterations. It's 1024 elements. Yeah, there's 1024 elements, 64 elements per iteration, and there's 16 iterations. There you go. There you go. Anyway, 16 iterations. We have to go through 16 times. So the way you want to program that is really up to you. There's a lot of ways to program that. But that's the important thing to note here is that when we load this vector, we're only loading in 64 elements. 64. V2 is, yeah, exactly, right? Assume S is in V2 is in S, or S is in V2. And the address of X0 is in R1. We also have to know how big the elements are. So if they're, we jumped up by 8 here, right? 8, and that's because it's a double. But if it's 64 doubles, right, then that's 64 times 8. So 512 is how much we'd have to jump up by, right? We'd have to jump up by 512, bytes. So if this was you have to put this in a loop, right? Because we have to loop through it a few times. Load vector 0R1, blah, 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 blah. I only went backwards here because that's how they did it, and I wanted to stay consistent with the solution here. But I usually like to go do loops forward. So you see I put R0, R1 is the address of X0, right? So, and I think for vector stuff, you have to go forward. It doesn't make sense to go backwards, like down the loop. So we start at X0. We load 64 elements, we add, we store, and then we branch, right? Branch here. Branch not, yeah, okay, so actually before we do that, we need to, we know it's 16 iterations, right? We know it's 16 iterations here. So I'm just going to load word into just like R2, or add immediate. I'm going to add immediate R2 0 with 16, right? So this R2 is just going to keep keeping track of which iteration, how many iterations we have left. So we have 16 iterations left. Just like in the middle here somewhere, I'm going to do sub I R2, and 1. Say 1. So we're going to subtract 1 from it so that it's now, it's 15 iterations. And then we're just going to say B, N, E, Z, R2 loop. So as long as R2 is not 0, then we can loop back up. This is how many iterations we have left. Okay. So this should work here. And I put it here, not here, because then you need like a branch delay. Well, we have a branch delay slot, but you'd need like a stall here. If you put sub I there, you need a stall in between it just because it needs a second. So instead we just do this, right? I just put it there. Doesn't matter. And then the number of cycles this will take is this will be 64 clock cycles. This will be 1 clock cycle. This will be 64 clock cycles. This will be 64 clock cycles, and this will be 1 clock cycle, right? So it's not like this is just 1 clock cycle. It's just that it's 1 instruction. So overall, right, this is going to be, a certain number of clock cycles, right? And it's going to loop 16 times here. So the total number of clock cycles will be, the total number of instructions are 1, 2, 3, 4, 5. So number of instructions that are going to be executed is 5 times 16. But it's not really that simple, right? Because these are different clock cycles. I will explain vector MIPS, Let me just finish writing this. So number of clock cycles is going to be, 16 times 1 plus 3 times 64 plus 2 plus 3 times 64. Because we have 2 1 clock cycle instructions and 3 64 clock cycle instructions. Okay, and that's going to be the total number of clock cycles there, which is whatever, some number. How come she didn't include add I, sub I, BNEZ in her solution class? Because I think she might have assumed that the whole vector can be put into the whole like array can be put into a vector, like a vector inside the system. That depends on the specifics of the question. So this will be specified to you in the question, like how many elements the vector registers can hold. It might be told to you in bytes as well. So then if you told to you in bytes, then you need to convert it based on what you're looking at, right? But like an integer is 4 bytes and a double is 8 bytes. Could you explain vector MIPS again? Yeah. So the vector is really just like that. We're loading. Hold on. I didn't update R1. Yeah, I didn't update R1. Sorry, got to update R1 still. So let me, before I explain vector MIPS, I got to update R1 still. So yeah. R1 is the address, right? We need the address here. So all I'm going to do is I'm just going to add immediate R1, R1, 512. I got to jump 512 bytes over because that's how long 64 elements are. So it's like I'm taking my long array, and this is going to kind of help explain Andre's question as well. Could you explain vector MIPS? So it's a long, this is our X. So our X array. And we're taking a vector, right, of size 64 elements out of it. Computing, then we're jumping over 512 because 64 elements is 512 bytes. And we're taking another vector. We're computing, right? 512 bytes. 512 bytes. And then we're doing that again and again and again and again until we get to the end of the array. So that's how vector MIPS works, is that we do things in these large vectors. The size of the vector is specified to you in the question. I'm saying it's 64 elements, 512 bytes. Okay. But that depends on the question. The question will tell you those numbers. Okay, so why don't we talk now about, we did that. I want to talk about these state diagrams, right? Because these state diagrams are definitely going to be relevant. She really made a big deal about cache coherency. Right?
Adam,
And
before that, just
yeah,
a quick
yeah,
question.
go for it.
For in the lecture notes, the latency is pretty much counted as if you're counting each instruction, right? Assuming each instruction is one clock cycle.
I guess, yeah.
So is that how we're going to do it, or how would we calculate the latency, for example, for the loop unrolling question? Do we just count the number of instructions and divide by 4, or do we?
Yeah, I would just count the number of instructions and divide by 4. That's
Yeah.
pretty much it. As long as I think as long as you explain what you're doing, just like write in words like what you're doing and how you're, and just like stay consistent, then it's okay. It'll be okay.
So in this situation would assume that each instruction takes one clock cycle and 14
Yeah.
clock cycle per thread. Okay.
Yeah. We assume everything takes one, which isn't actually true, right? Not everything
Yeah.
takes one clock cycle, like even pipelined and all that, but to activate. But yeah, like we assume just everything takes one clock cycle. Just count the clock cycles.
Okay. Thank you.
No problem. Okay, so there we go. So that is that. It's another question. Can we also go over write through and write back? Yeah, that's the state diagrams, exactly, right? The state diagrams, write through and write back protocol, exactly. So I don't know if I know these. I even know these too well. So it's good that we get a chance to go through them. Let's just like kind of go backwards here. So review notes, loop unrolling. We did that, right? And then example 2. What is example 2? What is this? Another loop unrolling? Let's just take a look at this. What is this? The following loop, yi a times xi plus xyi loop. So this is just doing that operation. A single issue, unroll loop, and schedule it. Assume ALU, ALU3, ALU SD2, ALU, like the latency between these two things, between load and ALU. Okay. Assume dual issue processor, so we can do 2 at the same time. I mean, she's posting this, but she never talked about this in class. So I don't think this will be relevant. Issue unrolling with loop unrolling. Okay, I mean, that's probably be good to talk about as well, but it's okay. Let's just see what this is. So this is just some kind of loop unrolling. This is the loop unrolling, or like just the loop. And then she draws the Gantt chart there. And then that was the solution for part A MIPS conversion. Probably finding the performance of the code with drawings. Okay, I mean, like, what am I looking at? What is this? It's just like the end of it.
Yeah.
So strange. Okay. Anyways, so then vector, we also basically talked about. Like, there's not that much to say in vector. It's really just like look at some of these code examples. Like that's what you're going to be expected to know what to do, right? Load vector, load. This is just loading a float. Load vector, multiply vector, add vector, store vector. It's really the same stuff. It's just like you do it, and it takes 64 cycles because it's usually size 64 vectors. Yeah, I see here it says 64. Assume vector register equals 64 elements. And it's in elements. It's in terms of elements, so not bytes. You convert it to bytes if you need after. This last example doesn't make any difference. Okay. So it's really just this multiprocessing stuff. So yeah, so we can look at the different challenges of parallel processing. Doesn't matter. Centralized types of shared data. So memory coherency requirements, two ways, write and val. Okay, so this is the stuff that we want to talk about. Basic schemes for coherency. Okay, snooping. All caches snoop. Okay. So write invalidate. The protocol maintains an exclusive access to a data item through invalidating all other copies on other caches. Right? So you just write an invalidate signal to all the other caches. Okay? So let's look at this example for write invalidate. Okay? Why don't we like make a slide of this? Like make this kind of try to condense everything here. So this is for write invalidate. Here's an example, and maybe we can talk about this example a little bit. Okay, so what's happening here? P1 and P2 are processors, each with their own caches, C1 and C2. They also have a shared memory here. P1 tries to read the variable X, but it's a miss. So memory, X equals 1, goes to P1 there. Then P2 tries to read X, and it's also a miss because it's not in the cache. And so memory, moves the cache block over there, and then we get that. P1 writes 5 to X. P1 writes to its local X here using WB cache. WB cache is write buffer? No. Word bank? WB. I don't know what WB means, but write using cache. Okay, I don't know. Using cache. If anybody knows what WB means here, I'm interested. But anyways, P1 writes 5. P1 wrote 5 here. Invalidates X in C2. That invalidates it. So the invalidate protocol, if P2 right now has valid data, if a different processor writes, then it becomes invalid. And this is the invalidate signal. The invalidate signal goes there. Then finally, P2 reads X, generates a read miss. So since it's a read miss, then what happens here, right? So the 1 here is still invalid, right? And then the read miss, because it's invalid now, it's going to just read, but I guess it's just going to read from C1. Why would it just read from C1? I thought it would just read from the memory. Maybe it writes to the memory and then it goes like that. Because the memory also should know that it has an invalid piece of information now. I don't know. That's kind of weird. But I don't really know why this is a 1 here. But considering the fact... Let's see. Is there any information on the next page here? No. That's all the information we get. So yeah. So, you know, maybe the diagram will help, right? Update. Multi-level cache, coherency. Where's the update? There it is. Right through. And then we have coherency protocol. And this is for using 3-state protocol. Write back. Write through and write back. So I don't think write and validate is that important. Because write, unless it's the same, maybe write and validate is the same. Yeah.
I
it's
asked
the same as
in the lecture.
Oh, and it's the same as what?
It's write back and write and validate are the same thing, but the state machine you just showed is missing a couple of transitions.
Yeah, is it?
Yeah.
This is right, what I said, right? Write and validate is write back? This is the same thing?
Yes. Yeah.
Okay, yeah. And this is for write and validate, which is write back?
Yeah.
What transitions is it missing? Oh, it's missing the bus transitions. Like these ones?
If you go down one more slide, you'll find the full thing. Yeah.
Yeah, that's the full thing. Yeah. There we go, right? So let's try to understand this diagram a little bit, because I think we're just supposed to just straight up just know this diagram for tomorrow. I think we'll be asked directly questions about the state diagram. So let's look at what's happening here, right? So if both of these things have invalid data, right? So if, you know, J represents some other processor and I represents the processor. So if I'm a processor with invalid data and I read, then I get my data becomes in a shared state, right? So shared state means that it's from the main memory. Right? It's coming from the main memory. Let's see if this is described anywhere here. What are the three? Here's the three states for write and validate. Why don't I make this example a little smaller? It's a little too big. She equals write back. So I'll make this a little bit bigger. And here's the meaning of the states, right? So invalid state, this copy has been changed by another processor write to it. Only bus write causes block to be invalid, right? So to go to invalid, right, then we have some other processor. You see how we're getting to invalid? Some other processor is writing to that variable, right? So if we're in a private state, but then some other processor writes to it, and there we go. Shared, processor reads a variable that is not in its cache. A read miss generates the state. So you see if we have a read from invalid, miss, right? Or a read miss, right? So that means RI. This is RI here, right? If it's shared and I read miss again, then it still is shared. Why don't we literally just draw it? Let's just redraw it, because I think that'll help us memorize it first of all, right? And let's try to draw all the different arrows here, right? So if I'm in the private on the bottom, then invalid, and then valid. So if I'm in the valid state, or no, what's it called? Not valid. It's called shared. Right? If I'm in the invalid state and I read, so RI, meaning me, the processor, who has an invalid block in the cache, reads, then that's going to be a cache miss. We're going to bring it down, and then we're going to get shared memory, right? Stuff that we read from. We're gonna get shared, which is basically valid. These are both valid, but specifically It's going to go to there. If I, is there any going? Yeah. So if I have invalid and I write to that variable, then I'm the only one that knows the new value of that variable. So it's going to become private. Private means processor writes to a variable causes the block to be labeled exclusive as other copies in other processors are invalidated. Right? So that means if I have shared and some other processor writes to that WJ, meaning some other processor writes to that block, then it becomes invalid for the same reason that this becomes from invalid to private. If I'm writing, then I just know that value, but everything else becomes invalid there. Okay, and then if I'm in the shared state, and I think also if I write to it, right? WI goes this way. No, WI goes. Oh yeah, no, sorry, yeah. If I still write to it, right? If I still write to it again, WI, then it's just going to stay private. This is just like as if I did it in the first place. And if I read from it also, right, then it's also going to be just like that. So it's just going to stay there. Now, what if I'm in the shared state? If I'm in the shared state and I write to it, and I write to it, it should become invalid. It should become private. If I'm in the shared state and I write to it, it should become private. Basically, if you're ever writing to a variable, it becomes private. That's the main thing. If you're ever writing to a variable, it becomes private. And if someone else writes, then it goes to be invalid. Right? If someone else writes, then it becomes invalid. Right? So maybe I'll write that down because that's kind of the important thing, right? And I'm using the word I and someone else as the two different processors, but I meaning the current processor, someone else meaning just some other processor. So if I write, then this will become, hello? Oh, I'm in French keyboard. There you go. If I write, then it becomes private. If J writes, let's say if J writes, then it becomes invalid. Okay, so we're going through it. All right, seeing what happens, everything here, right? So, how many arrows am I missing? Probably a lot. So I have that arrow, RJ. So if I'm private, yeah, okay. If I'm private, if I have a private variable, and someone else reads RJ, right? RJ, and someone else reads, then this means this is like what's happening here, right here, right? P1 has a private variable. Someone else reads. Now, what's going to happen is that variable is going to get moved into the cache, right? Because the cache is going to be invalid too, or in the higher level memory, it's going to be invalid there too. And then now it's shared. It's not private anymore, right? Because now another variable also has it, because then that other processor is going to get the write. What I'm writing to the shared memory, and then the other processor is going to read from that. So, but now it's shared. It's not private anymore. So we got that two, that two, that two, that one. We just have the looping back, right? So if it's invalid, and someone else writes to it, same thing, right? This is an I. Sorry. Oh no. Sorry. This is a WJ. Sorry, I have it a little backwards compared to the diagram. How about I don't have it backwards? Should go like that. WJ, so I don't get confused. So if it's invalid and someone else writes to it, then I'm still invalid, right? If J writes, invalid, so it's still invalid. Okay? And if someone else reads as well, right? Yeah, if someone else reads as well, then what do I care, right? Then it's the same thing. Question? No? Good. Okay. I thought someone said something. Then the next one, shared. Okay, so I know I'm looking at the diagram, but I'm trying to see if I can guess it without looking at the diagram. So what do we know? If someone else writes, if I write, then it either goes to that or that. What about reading, right? So if I read something that is shared, then it's still shared. I haven't changed it. So it's definitely not private and it's definitely not invalid. I'm not doing anything to it. Or if someone else reads J here, right? Someone else reads from shared memory. They're not modifying it. So it didn't become private, doesn't invalidate what I have. Okay, and that's the diagram. There's a couple of these like read, miss I, read, miss I, but that's basically part of my explanation, what I just said there. So a little a little complicated, a lot of arrows. I'm definitely going to try to draw this once or twice tonight. But that is the main spiel of what's going on here. Hopefully every arrow makes sense there. It's really just, you just think about a cache, right? Just think about a cache from 758 and think about what's going to make it a valid piece of information and what's going to make it not a valid piece of information. It's just that we have multiple processors now too. So other things can do it. So that's why this I and J notation is not bad. It's like someone else reads, someone else writes, and so on. Anybody feel free to stop me if I have a question. Otherwise, I'm just going to keep going. So that is the state diagram for the write back, which is the same thing as write and validate. Then the last thing is the write through coherency, right? So write through just directly, I think you just directly send the information. Let's maybe read this quickly for write through. Let's take a look at this. Write through cache coherency protocol. Valid and invalid. Requests are from local processor I for a read or write, remote processor J for a read or write through the bus. If state is invalid and there is another processor reading or writing to it, the result will be a no change. If the processor needs to read or write to a block and the state is invalid, the processor will change the block state to valid because you're reading from the cache. On valid state, processor can read and write to a block with no change in the state. But if other processor writes to the block, the state changes to invalid. So the point of write through is that you're going to like move the information with it. But the only way you know to trigger that with the bus is if it goes into the invalid state. So once again, maybe let's just draw this picture. So this is for the write through protocol, like that, write through protocol. So for write through protocol, I mean, I'll put the picture, but I do want to just kind of guess here what's going on. You know, if there's only two states, right, so maybe I'll scroll down a little bit just so I don't see the picture. Right, there's only two states, which are, why don't I use a different color, which are valid, use a green, valid, and invalid, same side. Nope, wrong side. Cheated that in lecture. Invalid and valid. Okay, so if I have a piece of information that is in the valid state and I, let's say, read from it, then it's going to stay in the valid state, right? Because if it's valid and I read from it, I'm not changing it. No one else is changing it. If someone else writes to that, if someone else writes to it, then it becomes invalid because it's basically they have a private variable now, but we don't call it private for write through. Right? So yeah, there you go. Right? Okay, so then now let's think about what's going to happen if some, let's maybe finish the valid state here. So if I read, nothing happens. If I write, still nothing happens. Right? It's still valid for me. It's still valid. It's invalid for everybody else, but it's still valid for me. And finally, if someone else reads, then there's no problem because it's valid. What I have is valid. If someone else reads it, they're not changing it, so it doesn't make mine invalid. Right? Now, if you're in the invalid state and you write to it or read from it, right? But let's first of all, if you write to it, then it becomes valid because now you have the most updated piece of information. But also, if you read from it, this is going to trigger a cache miss, and it's going to move the cache block. And then finally, we still have to say if something's invalid and someone else reads or writes, then whatever, right? Doesn't make a difference. It's still invalid. For the write even more so, and for the read, it just doesn't affect you because you didn't read it. And there you go. That is your write through protocol. Much simpler, just because we don't have a private state, so that's kind of get confusing. The private just means that you just wrote to something, and you're the only one with that information.
Do you think we're going to be asked to draw one of these two diagrams on there and maybe ask questions on it, or just redraw it?
Both, I think. Both. I think. I mean, I'm not writing the exam, but like, yeah, I think both would be a valid thing to do. One of the practice tests had this kind of thing where you had to know the diagram. They didn't actually ask you to draw the diagram, but they just asked you questions about the diagram, so you had to be able to draw it to know it. Yeah. So there we go. So that's let's see. Are we done this one? I guess state diagrams to know. These are the two state diagrams to know. Pipelining question, we did that. I guess I wanted to do a pipelining question, so we did pipelining twice, right? We did a little Gantt chart there and a bigger Gantt chart there, but yeah, we did that. And now it's really just other things that may be on the exam. So why don't I quickly go through? I haven't done this yet. I don't write beautiful notes for this course, but I do take a little bit notes when she's talking, just like things like, oh, this is going to be good for the exam or something, right? So we can go through a couple of these. Oh, my computer's freaking out a little bit. Okay, it looks like we're okay. So there's this one, which is exactly the one from the course, right? From this is exactly the one we just did, right? And that this lecture was basically entire that. And here's the vector one. Oh, here's the vector one. Load vector, load, add vector, store. So she really just, I don't know what I was drawing here, but she really just assumes that everything can be loaded in one go. So if you're given no information, you can just do something simple like this, right? Where you just like load the entire thing. RY is just like the address of Y. S, just load that. It's a floating point number, right? So you just put it into F0. Add vector, store, vector probably, not SD, but anyways. Loop unrolling, register renaming. Register renaming is what we're doing here. Like where we say F0, F6, F10, F14. That's register renaming. We're doing the same operation, but with different registers. Converting to vectored ASM, that's what we're doing right here. Could be a loop involved, I don't know, but that's it. What's this? This class, I got one picture. This is all I got this time, and it looks like it's yeah, just this. So there's our invalid, shared, and private diagram. Trend of technology, homogeneous multiprocessors, coherency protocols, write back, write through. Heterogeneous means CPU, GPU. Homogeneous means heterogeneous main memory. Ooh, there was a vaguely remember her talking about something like, got a bunch of pictures this time. Week 10. What did I write here? Oh yeah, 2D, 2.5D, and 3D architectures. That could be something. Okay, here's a couple things. Okay, question 1, final exam. Well, let's start at the top. That's our write through protocol state machine for communication between CPU I and J. Yeah. Shared memory bus architecture. This is like the homogeneous processor. Final exam. Question 1, write back through plus FSM. Question 2, homogeneous / heterogeneous multiprocessor. Okay, so this is the thing that actually I vaguely remember now and also being confused about. I don't know if she said this would be on the exam, but this might be just something that she talked about. So I'm getting some messages. Do I think we're going to get this exact MIPS question? I don't think we're going to get the exact one, but something very similar. Do I think we're going to get anything involving DLX architecture with scoreboarding? Definitely no scoreboarding, because scoreboarding is something else. Yeah. Scoreboarding is that's just from the slides, I think, right? So there's no scoreboarding. Scared for tomorrow? Yeah. Yeah, some people are here giving me some messages. Yeah, scared. Someone said scared for tomorrow. It's understandable. At some point, you just got to get a good night's sleep. That's my advice. Got to get a good night's sleep. And just make sure you can think properly. Can I post the week 10 slides in Discord? Sure. There you go. Okay, so yeah, let's take a look at this, because this has some other weird stuff in here that she was talking about, and I kind of was zoning out and I didn't really know what she was talking about. So, given some amount of CPU, GPUs, and performance counters, decide some mapping like SRAM, DRAM. And there's like throughput counters, write request counter. So it's like how many. So the throughput counter is like how many times this had to be used. The CPU was used, and then write request counter is like how many times this block was written to. So much here. Multiprocessors. What's the difference? Oh yeah, this whole section here. Write endurance problem in heterogeneous shared architectures. Write endurance SRAM. Write endurance.
For the mapping question, the professor mentioned that tasks with higher throughput is mapped to the GPU, and the tasks with lower throughput mapped to the CPU, and then the tasks with the higher write requests are in the DRAM, and the ones with lower write requests are in the SRAM.
And is that like, you think that's like all we need to know for that kind of question? Like, just
Well, that's what I asked her, because she mentioned that she's going to give us if it's coming, list of tasks that we need to map, and then she mentioned that usually higher if we were to map those, the higher throughput ones would always go to the GPU, and then for the cache stuff, the higher write requests go to the DRAM, because the DRAM is the write intensive.
yeah. Let me write what you're saying. High
Yeah.
throughput. Is there an H? Throughput.
I think just like that.
Yeah. High throughput equals GPU.
Yes.
Low throughput equals CPU.
Yeah.
Write intensive equals DRAM.
Yes.
Read intensive equals SRAM. Okay. And so did she give you any information about like what kind of question she'd ask about?
What I would assume is she would give us like a list of 5 tasks, and then we just have to rank like from the highest throughput to the lowest, and then map all the higher throughput ones to every GPU, and then Once you run out, all the lower throughput tasks go to the CPU,
Yeah.
and then
And how would we measure the throughput? Like if like
she would tell us. She would tell us. We
did
can't.
you say like, throughput is some
That's
number?
yeah. That's what I
Uh,
would assume. What she alluded to on the lecture, but
okay.
she kind of was very vague about a lot of this. And then the memory stuff, she kind of switched between the two. So as best as I can remember,
Right.
SRAM is read intensive, and then DRAM is write intensive.
Yeah. Here's someone saying in the chat, from my notes, I believe she said a question will be to draw those diagrams, not 100% sure. These kind of diagrams here. Yeah. It's similar to like the first video she made where it was like you had all those different processors that were in a orientation like that. Like you had the NOC one, but there was also the one that was more like this. So that's that. I mean, okay, I guess. So probably the throughput counters are just like there to measure the throughput. So she might say like, oh, there's a lot of throughput, like high value of these throughput counters. So you map them to certain things. Then, yeah, NOC and a heterogeneous processor. So yeah, so if she asks you something about a heterogeneous processor, then you want to draw something like that. And if she asks you about an NOC, you want to draw something like that. I don't know how many people also take 838, but we talked a lot about NOCs and 838, so it's same stuff. But yeah, okay. So I mean, that's that. That's kind of good that we mentioned that, right? So it's good to know that kind of stuff. So that could be on there, and that's basically the end of my notes because I guess I didn't take notes the other weeks, or maybe it was midterm or something like that. I don't know. I just didn't take notes. So that's that. Anything else you guys want to cover? Oh yeah, there was a question in the chat. Let me open the chat up again. Someone asked something. Yes, no problem. Someone's thanking me. No problem at all. Happy to help. So someone asked, can you label the differences between the hit and miss write back flowchart versus the one we covered? Oh, what do you mean hit and miss? Oh, like these things that say hit and read miss here? Slide 30 of multiprocessors. No problem. Have a good night. Good luck tomorrow.
Wait, what about the practice exam solutions?
Yeah. So okay, well, let me answer this. Let me answer this question first, and then I'll get to you on that. Yeah. Yeah. So this person's asking about this, right? Yeah. This and this diagram. Take the union of these two diagrams, you get this diagram. It's the same diagram. It's just written kind of weird, right? But like, yeah, if it's like processor read hit, this is the same thing as saying what was it? processor read hit. So that means that I'm reading and it's a hit. No, it's a hit. Yeah, it's a hit in the cache, so it becomes shared. Right? And so on. So basically what I'm saying is like, you just need to know this diagram. Right? This is really all we need to know. So should I memorize all three or just memorize the last one with the yeah, it's the same question. Just this one. Right? Just this diagram and then just this diagram for write back and write through. And then you should be able to kind of logic it out. But make sure that the read and writes also make sense to you here, right? That it's doing the same thing. But it is all described in this because you see it says includes processor and bus actions. This is just bus actions and this is just processor actions. But this is both processor and bus actions. So it's the same stuff. Okay, Andre, you had a question about the sample exam. So I'll open the sample exam. It's not a sample. She didn't post this. This is just from it's from 2012. A lot of stuff here is stuff that we didn't talk about, but there's a few good things here. Some numbers don't make sense. So to be honest, like a lot of it doesn't make sense. I think the solution's just like poorly put together. Like this doesn't really mean much, and this is just like a lot of the same stuff. But some things that are useful, like this could be useful, right? This is an example question that could be like using the diagram, right? So why don't we just like go through this quickly? That was really the only thing that I found useful from that, but so it says, for example, why don't I maybe squeeze this here, move this here, right? So it says, assume a shared memory multiprocessor uses write invalidate, which is write back. So it's a big diagram, write back. Snooping, whatever. Find the state of the cache block after each of the following operations. Bus read to private block in cache. So there's a private block, read from private block, right? So if it's a private block, right, and some processor tries to read from that private block, other processor tries to read from the private block, it becomes shared. Processor read miss to invalidate cache, to invalidate blocking cache. So if a processor reads, what did it become shared? So bus you can interpret as J and processor you can interpret as I in this diagram. Bus means some other processor is doing it because it's on the bus. Processor is I. So if a processor read miss to invalid block. So if processor is in the valid state, tries to read, becomes shared because there's a whole write through, not write through. Sorry, like the cache block will cache miss, and then the block will move in and all that kind of stuff. Processor write to miss, right? Oh, I can't read this. Processor write miss to private block in cache. So we look at the private block, and we look at I write, and this still stays private, right? Because it loops in private. So I write to a private block in cache, it still stays private. Bus write operation hit to invalid block in cache. So we're invalid. We are someone else is writing, it stays invalid. Someone else is invalid. It doesn't matter hit or miss, whatever. So that's how we like use this diagram to interpret these questions here like that. That's really all that I found useful from this practice test. Like I did some of the other ones, but it's kind of a mess. But... Okay, guys. Well, I mean, I had nothing else to talk about, but yeah. Question?
Adam, yeah, one more thing last second. Can you go over that one picture that she sent us on the email? The one with her drawing? Yeah.
That's true. Let's take a look at that.
I just have like 2 lines in that code that I didn't understand.
Yeah. So not that one. Oh, did she not? Oh, maybe it's just in the. No, maybe it's.
I think it's in the shell.
Yeah. Okay, so like one of these guys. Oh, probably this one.
Yeah. If you just download it and rotate it. Yeah. Oh, okay. Yeah. So do you see the second last I6 and I7? I just don't get the I+1 and J+1 correlation in that. So how does it?
Oh yeah. No. She wrote it wrong. so it's not adding one. It's basically the R1 and R2 are like the address information, right? For the index, right? They're not equal directly to the index. It's not like you're going 1, 2, 3, 4, but it's basically like it's keeping track of how many times we've gone through the loop. We have to jump by 8, first of all, just because it's a float. So floats have size 8. But we're starting at the end of the list. Somewhere here, it should say, assume R1 and R2 have the address of the end of the list. x 1,000 and y 1,000. And then from there we just keep subtracting 8 back. So it should not say that. It should be say, because technically she's not doing this. It's just a common alternative way. Where am I?
It should be like 1,000 minus 8 or something like that.
Right. It should, exactly. It should be, so the loop, what we're really doing here in the loop is we're doing 4 I equals 1,000, I greater than equals 0. Just make this proper semicolons. I minus minus, and it's equivalent, right? It's equivalent to this to the code, right? You're just doing it backwards. You're just doing it from the end of the list down, right? And that's how this is coded, but that's not what this comment says. The comment should say I minus 1, j minus 1. And it's 1 because it's one element, which is size 8 bytes.
Wait, so where is J in all this?
Yeah. There's no J. You don't need a J. Basically, it's just like, yeah. That's a good point. J. Okay. So R2, R1 has the address of X, big X, 1,000. R2 has the address of Y, 1,000. And so we just keep subtracting 8 back down. So it's like I is not even the right word to use here, because it's not like I. It's just like R1 is just and R2 are both keeping track of the address, this final address here. And so we keep just going backwards from there. I itself is never counted. We don't have a variable here that's going 1,000, 999, 998, 997. We don't have a variable that does that. It's just, we're just keep jumping by 8 this many times, right? And to figure out this number, you'd have to use 1,000, but we don't do that. We just say assume it's been set properly.
Okay. So essentially, like it's like a tracker for X of I and Y I, right?
But going backwards, starting at 1,000.
Iteration. Yeah.
Exactly, and then going 8 bytes backwards, because that's how big a float is.
And you would like add that up. So like 16 if you're doing loop unrolling in the next iteration.
Yeah,
right.
Exactly. You do you subtract 16 if you're going to do 2 loops at a time, like 2 iterations of the loop at a time.
Yeah. And I believe she would tell us like how much loop unrolling in the question.
Yeah,
right?
I'm sure. That would be too crazy to mark if everybody did a different number of loop unrollings. So.
Yeah, and also like there's a lot of assumptions to be made in this type of MIPS than like our midterm, because like we don't really do shift logic left when we get the address or anything. Right. So like
there's a lot of ways to do it. A lot of ways to like solve the same questions, and a lot of assumptions that you just state. I would just stick to coding in the same style of the slides, just because then that's how she's gonna mark it, and then it's the same thing.
True. Yeah.
She'll probably give you better marks.
Yeah, appreciate it.
No problem. All right. Let's see if anybody else has any questions. Okay, so someone in the chat. Is it supposed to be added or add for this example? I would say it is added, 2Ds, 3Ds, I guess. Yeah, so I guess I should say da-da-da. But yeah, with 3Ds, because it's add is just for ints, right? Is it okay for you to scroll up to the loop unrolling question you did? No problem. It's multiple pages, so I don't know what page you want to see. There's the loop unrolling part. I'll zoom in a little bit. That's the code we started with, and that's the loop unrolling, and that's the scheduled loop unrolling. I'll post the notes, right? I'll post it in the chat there, but that's that. No problem. Okay, guys. Well, If anybody has any more questions, feel free to let me know. Otherwise, I'm pretty much done for the day. I will just try to memorize that diagram. Okay, let's try to memorize these diagrams here, and then once we know that, we're good to go. And yeah, otherwise, how am I feeling for the exam? I'm feeling okay. I'm not too stressed. I mean, I think I know this stuff pretty well. That I can go in pretty confident. That's, I can't do that for every course, but this course I think I know pretty well. No problem. Have a good night. Good luck tomorrow. And good luck with the rest of your exams too. All right, guys. I'll stop recording.